lecture, I will give some proofs. Okay? So it consists of 3 parts. So the first is a convex analysis view on combinatorial optimization. So I assume that you know minimum spanning tree or bipartite matching. And here I'd like to explain what kind of convex analysis phenomena you can observe. And the second part, which is tomorrow, I will go into more technical parts of discrete convex function called L-convex and M-convex functions. And the third part is concerned with duality phenomena. So conjugacy and duality. So maybe for many people, conjugacy and duality means the same, related, but in discrete setting, well, now the problem I have to erase. Oh, my name? If you listen to me, you can fill in. So duality. I will explain the difference between these two. And these are quite general in form, and I will explain how they imply important result in combinatorial optimizations. Now the answer is this. Okay. So the first section today is ingredient of convex optimization. So I assume that you know what convexity is, but I'm going to single out some features that I'm interested in. Now, before going into convex, let's look at linear case, easier case. So nice features of linear programming. What are they? Just imagine before you listen to me. What should be the nice features of linear programming in connection to convexity? Maybe you know that feasible region is polyhedral. So feasible region, or maybe I should tell you what LP is. For example, something like C X subject to A X B A X. This type of optimization program is called LP. You know it. Okay. So feasible region is a set of x's that satisfies this inequality constraints, and they those points form a convex polyhedron. Okay? The convexity here. And everything is actually the consequences of this. But so you know simplex method. And at one point, if you have a feasible point, you want to know whether that point is optimal or not. And that can be done by computing the reduced cost. Okay? And reduced cost shows that that point is local optimal. So you cannot improve without violating feasibility. So this is a local condition, but it still tells you that this is global optimal. So here is a very nice phenomena that local optimality implies global optimality. This is the important feature of convex programming. So in simplex method, it is reduced cost by reduced cost. And what else? If you write this way, you can write something else here. Can you write? Maximize something. It's dangerous for me to write because I'm going to make a mistake, but let's try. Maximize by subject to a times y smaller than c and y. Okay, so this is called dual program. The important point here is that given some object, you can associate a pair called dual. Okay, dual object is associated. So primal program is associated with dual program. Then you can consider dual of this dual by changing signs, etc., and you can pack to this original one. So dual of the dual of dual. Actually, that is a primal program. So here is an interesting phenomenon. But at this moment, we do not know whether these two optimal values are equal or not. I'm not saying that. I'm just saying that given a program, given an object, we can associate something else. Then you can associate something else, which is actually the original one. But as you know, that these two programs has a stronger relation called strong LP duality. So this is minimum equals maximum. Okay? This is an important phenomenon. And finally, if you have learned mathematical structure that explains this phenomena, then you know that this comes from separating hyperplane, the Farkas-Lemma. Okay? So Farkas-Lemma is actually theorem of separation. So in LP, we can enumerate such nice features. After these features are those features that I want to generalize in discrete convex analysis. So let's give some names for your easy memory. This is called convexity somehow. Don't take everything's so precise. The important thing is to understand the general idea. If you want to verify the details, I'm often telling small lies. Okay? And here is a local equal global property. And this is, say, dual object. Okay? And this is the minimax theorem. Actually, this is called duality. This is also duality, but these two should be distinguished. And finally, this is called, say, separation. Okay, so this is what we know about linear programming. Then, now we look at the convex functions in one variable. Okay, 1, 1, 2, univariate discrete convex function. So it looks like, if I draw a graph, it is, say, defined on integer points, like this. And so univariate means there's only one variable, okay? And this is f. So we can plot f by dots. So this is graph. So far, I didn't define what convex function mean, but I want to listen to your opinion. Is this function convex? From your common sense, it's yes. And then I can draw another picture which you say that this is non-convex. Okay? Then we can formulate this definition. So in discrete setting, in this case, if we have only one variable, the definition is obvious. I see no other possibilities. So the definition here is the following. So function, say, f, z, and now maybe the value is real. Or maybe bar. Bar means real or plus infinity. But for today, just easy to erase a bar for simple comprehension. And this is called convex. Say f is convex in our sense. If and only if the following is true, there we have such an inequality here. Okay, that was what you had in your mind without knowing. Actually, if this takes infinity value, then this might involve infinities. But our convention is this is true if one of these two is infinite. Okay? So this is the definition, convexity definition. But what you observed already here, if this is true, we can connect the points to obtain convex function. So here we connect them, and you connect them. So the yellow graph is an ordinary convex function. okay, in real variables. So it shows that it's a small theorem, theorem 1, related to convexity. So remember our denotation. So if F satisfies this condition, this implies that F can be extended to convex function. Here I don't write quotation because this is already defined concept. Okay? A convex function in real variables. Now actually this is if and only if. So we have a theorem showing that we define some convexity somehow, then it is compatible with the convexity that we already know. Then how about a local global property? Is the local optimal global optimal in this case? Sure, because it is extended convex function. So if this point is locally global in the sense that among the 3 points, this is minimum, then this is minimum overall. Okay? So we have local global property here. Means that if fx is smaller than or equal to the neighboring point, then that point x is a minimizer. Okay. So in this way, univariate discrete convex function is a very easy object. Okay. But I'm doing this because I want to generalize this story to multivariate functions. Then, how can we define the dual object? Well, like that, we don't have such a program. We just have a function f. And we want to associate with this another object, which is dual to this. And there is a general construction in convex analysis. And we can use that idea by simple adaptation. So that is called a conjugate function. Okay? Or maybe should I? So here maybe. So suppose we have a convex function, whether continuous or discrete. Maybe it's easier to draw a picture in a continuous case. So suppose we have this. Suppose this is f. And let's draw tangent line like this with slope p. And you change the slope, you can draw many lines. Okay. So for each line, we have a slope, say p, and we have a section here. So section here, the y coordinate, is a function of p when we fix f. So this coordinate is a function of p, and say call it phi, but depending on f. Now, we started with red curve and have drawn yellow lines. Now, erase the red curve. So just pretend that you are colorblind to red. But still you can see that there is a curve here. This is very interesting because if the starting curve is not convex, what happens is this. Let's say this is non-convex. And let's draw tangents. Fine. But here you will have such a tangent. So what happened? And if you erase the red curve, you can restore the original curve. So we could do it because the starting curve was convex. Okay? So this intuitively shows that this function from p to phi, this gives this curve, has the same information as the original function f. So this is the Legendre transformation. So in formula, so it's easy to write that after this is negative sub p x. Yes, if you, it's easy exercise for junior high. And in convex analysis, people write this function as f something. By convention, we have minus here. And this shows the transformation of f somehow. This can be asterisk. Okay, often. So this is a transformation from a function f to another function. And it turns out that this function, new function, is also convex. To see that, so here, maybe I should write it down here. To the definition, supremum over x, px minus f of x. Okay. And this is a function in P. X is a parameter here. Px minus fx here is a constant when viewed as a function in P. So this is a affine function, linear function. And taking the maximum of linear function, we get a convex function. Okay? So this is easy to see. This is a convex function. What is interesting is that so now this is a convex function. We can apply the same transformation again. Okay? Starting f, we make a conjugate. Then we make again. What should happen? Should coincide with the starting function. Of course, we can prove it. So this is an interesting phenomenon called biconjugacy. So in analogy, I could say that starting with a primal problem, you make a dual problem like there, and you make another dual, then you return to your starting point. So this is a phenomenon, famous phenomenon in convex analysis. So here we'd like to do this over integers. So remember that we are working on integers. What should we change? So first, in considering this phenomenon, I assume that f takes integers. Okay? So now f is an indiscrete function defined on integers. And p here is also integers. So what happens if p is an integer, x is an integer, so this p times x is an integer. And this is integer value. So supremum is taken over integers, so the value itself is integer. So this construction shows that this function is the same type of discrete function. And then that makes sense. This makes sense. So if I have time, maybe I can prove this, but probably it's better to proceed. Okay? So now the problem. Well. Okay, pretty good. Yes, but still not perfect. Okay, so now, I'll state as a theorem 3 as this. So now f is assumed to be integer valued, and then define this function by supremum of x, but x is now integer here, and px times minus f of x. Now p is an integer. Then f is convex. If x is convex in the sense of there, then this also is convex, and if you apply that twice, you restore the original function. Now, so this should be called dual object. What else should we have? We must have something similar to Farkas lemma, separation type theorem. And then that is geometrically easy. If you have convex function and concave function, say G, then separation theorem said that if f is convex and G concave, concave means that minus G is convex. That means that that inequality is reversed. And fx is greater than gx for any x. So it looks like this. F is above G.
G could go, maximum of G could be bigger than minimum of 1, right?
You mean this way? Oh, I understood. Okay. Yeah, yeah. Okay, you're right. It's better to draw that figure. What you mean is that what to do. Okay. So what you said is that so the minimum of f can be smaller than the maximum of G. Okay? But point-wise, for each x, f dominates G. That is assumption. And if you consider the case that involves infinity, so we need some technical assumption that domain of f means a set of x's at which f is finite. And domain of G is non-empty. Then if this is the case, then you can find an affine function in between. There exists alpha and say p such that fx. So this is a sandwich theorem. I left some space. For what? Good. So I insist that that should be integer and that should be integer. Okay? If you do not request alpha to be integer and p to be integral, then the statement is almost trivial from convex analysis. We consider convex extensions like this, then you can draw a line as a standard result from convex analysis. But here we would like to have, for some reason or other, integers. Actually, that makes sense in many cases. And why this is the case? There are a number of proofs, but if you, so in this case, for example, take the minimum distance. So here we have a minimum distance at x star. And here we can draw a line, possibly with fractional slope. But the feasible slope, the admissible slope, are actually integer interval. Because here we have an integer slope, because this is 1 and this is an integer difference. So slope here is integer and slope here is integer. So with respect to f, we have some integer interval for this possible slope. And also for g here, we have this slope and this slope, so we can choose. We have another interval determined by g at this point. Then we already know that these two intervals intersect because there is a fractional slope. So two integer intervals intersect, then there exists an integer point, common point. So that is this P. So this proof technique is, for this case, is simple. But in higher dimension, it comes to the integrality polyhedra. So it's important to know how this can be proved. Any questions? I have one more theorem, but maybe. This is important because it's starting. And at the last, in the third lecture, you don't have to, but please follow this lecture. Okay. This is a non-technical lecture. Is it okay? Then finally, the fifth theorem. This I call separation. And theorem 5 is a minimax theorem. So if we know this, the following is easy to derive by manipulation. We consider minimization, but maybe infimum, of function f minus g of x. F is convex, g is concave, so that these differences are somehow convex. And infimum is taken over integers. So this is a primer program. Then it should be equal to maximum of something. So we have introduced dual object. Okay? And this is defined for convex function. Yes? And for concave function, it's convenient to define the dual object by this. G is minimum over x, px minus gx. Okay, so g is concave, so the here is convex, so we can minimize. And the notation here, actually in conventional book of convex analysis, both of these operations denoted by star. It depending on the context, we have to decide. But now we have tech, so we can distinguish these two. In old days, there was only one symbol that can be put on the shoulder, maybe. Okay, so this is a definition, so similar to this. And the dual object here is G conjugate minus F conjugate P. And P is taken over integers. Okay? So this is easy to derive from here. So maybe in an exercise. And this is a convex minimization. This is concave maximization. So that makes sense. Okay, so this is a theorems that we should generalize for multivariate discrete convex functions. So these are the prototypes. I'm not saying that this is the old theorem. But the idea is important. Any comments or questions? Yeah. So this is called minimax. Then let me go on. I erase again. Oh, by the way, on the web page of this workshop, I put some supplementary reading material and also a problem set. The problem set is almost easy, but at the last there is some problem that I want to solve. Actually, that problem was asked by Andreas Frank several years ago, and we are trying some often, and we often forget the problem itself. So there is a problem, actually. So if you were interested, and if you cannot find that page, maybe you can just go to my homepage, Kazuo Murota, and then you can also find HIM material. So you can download there. Do we need more water? I don't know. Yeah. I've heard that this is videotaped, and I hope that people do not enjoy my clumsy raising. Well, okay, so now second part of today's lecture is convexity aspect in combinatorial optimization. So let us start with minimum spanning tree. Maybe I can assume that everybody knows what it is. So given a graph like this, with edge weight or length, okay, G and edge weight, then we have to find the spanning tree that has the minimum total weight or length. So in this case, for example, this may be the minimum spanning tree. So now I'm going to explain the local global property. The local optimal means global optimal in convex analysis context, but here also we have the same phenomenon. How can we verify that this T is the minimum spanning tree? Okay. So there is a standard result that you consider those arcs edges outside T. And then, for example, if you pick this E, then you consider a fundamental circuit, and take any edge F. So E is not in T, and F is in the fundamental circuit of T of E. Then what should happen? If this is minimum weight, we should not be able to improve the weight or decrease the weight by exchanging E and F. Okay? Since F is in fundamental circuit, if we take E and then throw away F, then we still have a spanning tree. But if that is not optimal, then the weight should not decrease. So what we have is this. Weight of E here outside is greater than or equal to weight of F. So this is a well-known condition for minimum spanning tree. But alternatively, we could write in this way. So T, weight of T is smaller than weight of T plus E minus F. This is another tree, but close to T. So this, in a sense, this is in a neighboring tree must be worse or equal to your tree. And this is the local optimal condition. If you understand that this gives a neighborhood, okay? This is local optimal. Local optimal equal global optimal property. And such condition is true in general in matroid. Okay? So any of you know the definition of matroid? Who knows? Then who does not know? Okay, then I will explain at least definition. Okay, definition. Actually, definition itself is most difficult thing that we can understand. So often I say to the students, the definition itself is the final goal of mathematician. So first, even if you cannot understand the definition, you should go on to understand the theorems. So then theorem shows you how that concept behaves. Okay? So then you will know what that concept was. But mathematician should start with definition. Okay, okay, so matroid. Okay, 1, 2, 2, matroid. So it is a set family. So given, say, E is a finite set, in this case, edge set of a graph, particular graph. And say B is a family of the subset of E. This is notation for that. I'm going to define base family, okay? Such that B as a family must have some property. So if you take two sets, x and y, from B. Any xy in B, that means any two spanning trees. And if they are distinct, there is an element x. So for any x in x minus y, then the following should be true. Well, the first is x minus x. There exists y somewhere here such that x minus x plus y is also in the base. This is one of the definitions of matroid basis. And in the spanning tree case, actually it's easy to prove this. And there are the variants of this axiom. So this is one of the most famous form. But instead of this, we can replace by you erase this, and you replace by this. This is also the same axiom, equivalent axiom. Okay, so maybe I now realize that it's better to write this way. Yes, that's what I'm going to write. Okay. Then number 3 is that this is true. And this, instead of this, we could say this is much stronger. It looks, but actually they are equivalent. Okay? And for discrete convex analysis, this form is most important. Okay? Well, so this is matroid. Very abstract notion, difficult to understand. But for this setting, we have a similar phenomenon. So we can consider minimum spanning tree type problem. That means minimize weight of x subject to x is a base. Here, W is the weight function. And for this, a famous algorithm is greedy algorithm. But today, I don't discuss it. But instead, I say that this is also true. So local optimality condition, in this sense, implies the global optimality of a base. Okay, so Theorem says if so x is a base and x is smaller than any neighboring base. So our convention is that if this is not a base, then this value is plus infinity. Or more precisely, for any x, any y, any outside x, such that x minus x plus y is base. So this is the local global theorem. Sorry?
If that false, then x is also
Yes, you're right. Then W of x, well, how did I write? for any base. This is global optimum. Now, so this is a local global property. What is a dual object in matroid? We know we have defined this. So this is a family of sets. And also you may know that subset of a base forms an independent set. This is also a set system, but characterized by similar but different exchange axiom. But what is different, completely different in nature, in terms of duality, is rank function. Okay? So if we have B, we are going to define a function on the set function according to the following formula. Rho of A is a subset of E, is defined to be the maximum size of intersection with a base. So A is any set, can be very big, can be small. And you want to find the base in this family that has a maximum intersection. So this defines a function in A. So this is called rank function. And in a sense, we have, so this is the intuition behind. Given the basis family, we have constructed a dual object according to this formula. But then we are interested in how we can come back. Not the same operation, okay? Doesn't look the same. But we want to come back here. How can we do that? So that means that given a rank function, now how can we define basis family? So this is well known. So namely, given this function, now we are going to define B as a family of X, or maybe I should have written X here. X such that O of X equal to O of E and O of X equals to cardinality. So that the second condition means it's called independent. And this is spanning. So spanning and independent means basis. So the point here is not this concrete formula, but given rank function, we can construct set family. And if we start with B there and row from B, then we construct this, we obtain the original set family. So in a sense, we go from basis family, make a rank function, and we come back to the original family. And the family B has some property, exchange property. So that property must be expressed in terms of rank. Then it is known that rank function have the following property. One is rank function is non-negative, of course, and bounded by the cardinality. And second condition is monotonicity. Monotonicity means x, y implies OX smaller than or equal to OY. These are sort of, yes?
The rank function is the dual of which function?
Okay. Good point. So I have written in this way, but in this construction, so far, I didn't give the function. The role of function is just a b. And if you want to represent b as a function, then you can define the indicator function that takes 0 on b and plus infinity outside b. This is a function. And actually, if you apply that Legendre transform to that function, you will obtain this. So this is the story behind. But so far, I didn't enter into such details. Okay? So this corresponds to B family as an object, and this corresponds to whole. Okay? And now the last property is famous. You should all have already known from your previous lecture. What should it be? Say again? Yeah, good. Submodular. Submodular. So the conjugacy here inherent in matrix is that the family of set functions satisfying these conditions and the family of subsets satisfying that axiom have a one-to-one correspondence. Okay? And that correspondence can be expressed in this Legendre transform, okay? Which I will explain later. Any questions? So what I want to say here is that also in matrix theory, the convex analysis concepts are underlying. Maybe you have never, say, realized, but it exists. Okay, I have 10 minutes more. Then I'm going to bipartite matching. Not really. Well, it's a mess. example. So bipartite matching looks like this. We're given a bipartite graph, and you want to find a matching. Let's assume that we are concerned with perfect matching, like this. Okay. And now assume that we are given a weight on edges, maybe non-negative integers, assume. So we want to find minimum matching where M is a subset of edges which is matching, perfect matching. So we assume that we have same number of vertices. Now, what is the optimality criterion? When do we know that given matching is optimal or not? Of course. Sorry? Yes. The alternating cycle is a standard technique. So if you have a perfect matching, I don't care how we have found that. We are just verifying the optimality. So direct the perfect matching from right to left, and other edges from left to right. So we have a directed graph. And we assign the length. So here we negate, because it is reversing. The original h is weight f, the given weight. And what is known is that matching M is optimal or minimum if and only if there exists no negative cycle with respect to this length function. If there is a negative cycle, then we can improve. So that is, the existence of negative cycle means it is not locally optimal. So it cannot be globally optimal. Okay? So improvement along negative cycle is a local improvement. So what is important is the converse. If the matching has no negative cycle, then it must be globally optimal. How can we prove that? There are many ways. The standard way maybe is to use LP formulation plus integrality, like total dual, not that difficult, total unimodular coefficient. Then we can argue that that is the case. In particular, we could use dual variable potentials associated with vertices. So this is a standard way of thinking. But here I interpret this phenomenon as a local, in the context of local global optimality. Okay? But this type of local optimality is different from what we have seen with minimum spanning tree. This is more complicated. It involves more elements. And actually, this type of improvement is also valid for majored intersection. If you have a major intersection, you can construct this type of graph, and there is an optimality criterion saying that common base is an optimal if and only there exists no negative cycle in that graph. Okay? So let me just write the problem itself. So given two matroid in terms of basis, matroid. And the program is to minimize x, weight of x, and we're given weight. Maybe non-negative integer for some reason that we'll show later. Minimize the weight subject to x being the common base. Okay. This is matrix intersection problem in a form, in one of the forms. Okay. So here I mentioned negative cycle criterion. Oh, well, you can choose. This is if you like, I can change. If you like, you can make a dual of it, one of them. Yeah. I think still it makes sense. Okay. Or maybe I don't mind following the audience opinion. So, but in convexity, it's yeah. So now we agreed on the minimization. So what is known here? Here I talked about negative cycles, but there's another important result due to Hausdorff called weight splitting. I will explain what it is. Weight splitting theorem. This is not weight. This is not splitting off. Okay, weight splitting. Hausdorff. Okay, so x, which is common base, is optimal or double minimum. Minimum with respect to this weight, if and only if there exists a division of weight into two vectors. Maybe. This is called weight splitting, where each vector is an integer vector, okay, such that x, oh yes, x is a double one minimum in the first matroid, and also the same is true for the second matroid. Okay. And in this context, this corresponds to finding the optimal potential associated with vertices. Okay? So this bipartite matching program can be formulated as an intersection program on edge set. And because of this theorem, we have vectors on edge set. Then for each vertex, we have number of edges incident to that vertex. And on each edge, we have weights, W1, W3. Then we take the minimum of them. That defines the potential here. Okay. So now this is an important theorem. But actually, what is the nature of the theorem? It is true, and it can be proven in several ways, maybe using TDI-ness, total dual integrality, or algorithmically we can construct the splitting. But from convex analysis point of view, this splitting gives us actually separating hyperplane. So as we wrote in this way, well, we claim that there exists some hyperplane separating these two. And this separating plane corresponds to this weight splitting. So I have no time to explain the details, but I just want to point out this important theorem is also a separation theorem. Okay? And maybe if you're interested, this is explained in my book, so you can consult it. But the point here is that all these familiar important results can be understood in terms of convex analysis. Okay, so that is my message for the first lecture. And if you have any questions, you're welcome. Please come to me.